Hi, and welcome back to Covid-eos. My name is Ioana Bouros, and today we'll continue our journey in understanding compartmental models in the context of epidemiology by looking at an actual model used by the UK government in order to support their health policy decisions, such as the institution of lockdowns. In the previous two videos of this series, we have looked at what exactly are compartmental models, as well as some very basic examples of epidemiological models using compartments. Though very important and powerful tools of their own, these structures might be too simple in order to replicate some of the more important factors governing the transmission of the virus. For example, teenagers and working people, they have per day a larger number of contacts than, say, someone in their 80s. Therefore, they are more likely to transmit the virus than their elderly counterparts. Similarly, school-aged children interact more with people their own age per day than, say, their parents. Therefore, if the epidemic were to occur in a school, it will first spread throughout the children, and then their parents, and then outside within the community. Hence, it is clear that not everyone in the population interacts the same, but according to a so-called contact matrix. Here, we can see a representation of the average daily number of contacts people of different ages have across different regions of England between February 2020 and June 2021. The grey blocks represent the lockdown periods, and we can definitely see a qualitative change in the behavior of the population. Keeping in mind how very differently the virus affects people of different ages, we might want a more fine compartmentalization of the population. The model created by University of Cambridge in collaboration with Public Health England, which we will call the PHE model, and you can see a link to the paper here and in the description, is a deterministic compartmental model with spatial structure. That is, it models England as 7 different regions, which somewhat relaxes the assumption that the population is well mixed. This model makes use of the concept of contact matrices and assumes they can vary in time depending on the restrictions present at the time, such as lockdowns. This model is similar to an SEIR model, with the exception that instead of having only one exposed and one infectious compartment, we have 2, with the following rates of transmissions between the compartments. The time-dependent rate at which susceptibles become exposed depends on the current contact matrix, as well as both the number of susceptibles and total number of infectious individuals at that time. The rate at which individuals move between the compartments is inverse to the time spent on average in that compartment, so we assume that the two E-compartments are identical, hence why we have the same rate here. Similarly for the I-compartments. The explanation for why we choose to have 2 compartments instead of 1 is that we wish to create a time delay in the shifting of the exposed individuals to the infectious and subsequently to the recovered compartments, like this, which will make the model more realistic. The L is the latent time, or the time between being infected and start being infectious, and the I is the infectious period, or the time between becoming infectious and fully recovering. What we mostly are interested to find out using this model would be how many deaths we could get daily over a period of time. However, the PHE model does not have a compartment for deaths. To compute the number of deaths on a specific day, we use the daily number of new infections that have occurred in the days leading up to the desired time point, and the probability distribution of an infection resulting into a death after a given number of days. Also, as we have mentioned in the bonus video on solving an SEIR model, the outputs of the model depend very much on the value of the parameters we choose. We can see here that by changing one of the parameters of the model, we get very different behavior in the number of deaths. This figure was produced using my open source reimplementation of the PHE model as part of my PhD. There is a link to the repository in the description of the video. The PHE model was actually used by the government, together with a few more, to validate and motivate the restrictions imposed during the more critical times of the UK epidemic. As with these rather simple extra assumptions, it was able to make reliable predictions of the number of deaths and new infections. This brings to a close this series on compartmental models, and hopefully you have now a better understanding of how compartmental models play into epidemiological modeling. Thanks for watching.